One thing with moles is we've talked about how it's just a number, so it's like 12 or a million, but it's a really big number. So this at the top is 1 mole written out in all its glory. That's a lot of zeros. For comparison, underneath it, we have 9 million or 9 billion. That is, yeah, that is roughly the population of the planet. Now, if we had 9 billion planets, one planet for each person on Earth, and each of those planets had 9 billion people on it, it would still be less than 1 mole. Okay, so that is a huge number. So we might think, oh, well, gosh, if that's a lot of atoms, that must be a large amount. But the fact is the atoms are really, really small. So I have some samples that are 1 mole, and some of them are floating around. I'm going to grab these two right here. So this is 1 mole of aluminum. So it fills the jar not quite halfway. So this many atoms doesn't fill the jar quite halfway. And then this is lead. And it's a little bit, maybe right at halfway. So it fills it a little bit more. So same number of atoms. Now, why would the same number of atoms have a different volume? Could be different mass, but it's more different size. Like the volume that 5 babies take us up is not the same volume that 5 football players take up, because the football players are bigger than the babies, theoretically. Well, maybe we have teeny tiny football players. Okay, the other thing is connected to what you said, mass is important too. So this is how we know how much to put in. We can't count these atoms. They're way too small to even see, let alone move around with tiny little tweezers. So we have to use the molar mass on the periodic table to weigh them out. So 1 mole weighs the amount that's on the periodic table. So this is aluminum. If you look at aluminum on your periodic table, this weighs 26.98 grams. That's how we figured out how many moles are in here. What is the mass of the lead in here? Lead's near the bottom, it's PB.
207.2.
Yeah, 207-ish, okay? Now, you can tell that difference. I'm going to pass this around so you can feel it. Even though there's the same number of atoms, they weigh quite a bit different. So if you hold those two, which one's good? Yeah, you can pass that around so you can kind of see how that works. Okay, so that kind of ties into density. We'll talk about density in just a second there. So here's another element, sulfur. There's 1 mole of that. This is sodium chloride, salt. Now this has 2 moles of atom. If this is 1 mole of sodium chloride, why are there 2 moles of atoms? Atoms. It's sodium chloride. There's 2 different elements, right? So there's 1 mole of sodium and 1 mole of chlorine. Okay, so we have twice as many atoms in here, but it's 1 mole for this number of formula units of sodium chloride. Similarly, this is the one that usually surprises people. This, which is filled up to right about here, is water. 1 mole of water. This number of molecules of water, which has 3 moles of atoms, right? 2 hydrogens and 1 oxygen, 2 moles of hydrogen, 1 mole of oxygen. So this, a swallow of water, has 1 mole of water. Okay. So atoms are so small that we can't measure out the atoms 1 by 1. So we have to use grams and we have to use volumes. But when they react with one another, they don't react by mass. Like if I were going to make a compound that was 1 aluminum and 1 lead, I couldn't just assume if I have 50 grams of each, it's going to be equal numbers, right? Because the aluminum weighs so much less than the lead does. So that's why we have to convert between grams and moles to get to units where they're all the same. They're all individual units. Okay, so we have three ways we can talk about amounts. How much stuff is there. We can talk about the mass, which we usually do in grams. We can talk about the volume, which we usually do in milliliters, and we can talk about moles. And there's no special unit, we just say moles, we're counting them. And sometimes you'll see kilograms, but for our chemistry class, it's almost exclusively going to be gram. Volume the same way. Sometimes you'll see liters, but we'll use almost exclusively milliliters. So this tells us how much of something is there. And if I report it in grams versus volume, the number might be different, right? I might say that this is 207 grams of the lead, but this might be only 50 milliliters. Okay, different numbers, but it's the same amount, right? It's still the same number of atoms of lead, whether I'm reporting it in grams or milliliters. Okay, so we've talked about how to go between mass and moles. Can we go between volume and mass? Yeah, what do we need? You actually do. I know you all know this, but you're just not thinking of it. We need density. That makes sense? So density, calculation-wise, is mass over volume. To remember the formula, mountains over valleys. Mountains are tall, it goes on top. Valleys are low, it goes on the bottom. Okay. I had somebody show this to me 15 years ago, and this is how they like to remember to do the calculations. You just have to remember where to put these things. So you draw this into a circle, and then if you're looking for density, you cover up density and you get mountains divided by valleys or mass divided by volume. If you are looking for mass, you cover up mass and you get density times volume. If you're looking for volume, you cover up volume and get mass divided by density. So a little shortcut there. This is usually reported in grams per milliliter or grams per centimeter cubed. Those are defined as being the same. So 1 milliliter is the volume, 1 centimeter cubed. And if we're dealing with gases, because gases are so much less dense, we do grams per liters, but gases aren't until the middle of October, so we're not going to worry about that right now. You should know, this is an expectation that I assume you know, that water has a density of about 1. So we just assume 1.00 grams per milliliter. And so what that means is that if I give you a volume, 1 milliliter is 1 gram, 20 milliliters is 20 grams, 17.5 is 17.5. Makes the conversion easy. In your lab early in the semester, you looked at the density of water. Is it actually 1.00? Not necessarily, right? So you have that big table of all of the numbers, and some of the numbers were like 0.999873 or whatever. Depends on temperature. It's the most dense at 4 degrees Celsius. So usually when a lake is frozen over and then there's water, we can assume that the bottom of the lake is at 4 degrees Celsius because that's where the water is going to be the densest. So if something floats on something else, the number would be smaller. So any number bigger than 1 is going to sink in water. Anything with a density bigger than 1, anything with a density less than 1 is going to float on water. So let's say I have lead, which has a density of 11.4, right? So that's 11 times that of water, 11.5 times that of water. It'd probably sink in water, right? Which doesn't surprise anybody. Gold, y'all know gold is heavy, right? Gold is about 19. And mercury is about 13.6. So we have a block of lead, a block of gold, and then we have a beaker of mercury. Why do we have a beaker of mercury instead of a block of mercury?
Liquid.
It's a liquid. So mercury is one of the only liquids on the periodic table. Bromine is a liquid at room temperature. So we have those. And so I'm going to have this beaker. I'm going to make it not so cold. Let's talk about this one. We got mercury in here. And then we're going to put a lead block in there. Is that lead block going to float or is it going to sink? So what we have to do is compare the two substances, lead and mercury. Which one's more dense, the lead or the mercury? The mercury. So the lead will actually float on the mercury. So our lead block is going to stay up here. And then we maybe put our gold block in. Is it also going to float? No, because this is a bigger number, so it's going to go down to the bottom. Our gold block will sink. Okay. So those are the relationships between density there. I think that's all I want to say on that. Okay. In the next, or in chapter 1, we skipped over the stuff on measurement. In section 4, there was some information on significant figures, which we talked about. We've incorporated a little bit more with the calculations as we've gone along. Section 5 deals with how we measure things in the metric system. Most Americans really kind of struggle with imagining how big or small something is using the metric system. So I'm going to give you some benchmarks. We're not going to translate. I'm not going to have you convert between inches and centimeters or between pounds and kilograms, because everything you do in the lab is already going to be in the metric system. But I want you to have a sense of how big things are. So when you're told to pull out a 50 milliliter beaker, you know roughly what size you're going to use. All right, so this is in chapter 1, I think section 5, measurement. A kilogram is 2.2 pounds. Roughly a book. Kind of depends on how big the book is, that kind of thing. So if you're talking a chemistry textbook, that's probably a little bit more than 1 kilogram. But if I'm talking about something like this is probably less than 1 kilogram. So in the ballpark of a book. So a newborn baby is probably going to weigh more than 1 kilogram, but probably not more than 100 kilograms, right? Okay, so an adult probably doesn't weigh more than 100 kilograms, depending on who they are. Big football player or whatever, might be looking right around 100 kilograms. But a newborn baby, no way. Something you use in lab, a gram is going to be about the mass of a paperclip or a raisin. So if you have to weigh out something in lab and it says weigh out 0.1 grams, are you going to use a big old spoonful? No, because you want something that's less than 1 gram, and a paperclip's going to be less than that big old spoonful. So you're going to start off with just putting a little tiny amount on there, right? But if it says weigh out 20 grams, you don't want to just put a little tiny amount on there because you'll be going all day doing little tiny amounts. So that's where it's useful to know roughly how big things are. All right, a centimeter is about the width of your pinky nail. So from here to here. Now, if you are, one of those people that have delicate piano player fingers, maybe the whole finger is 1 centimeter. If you're somebody who, exercises your pinkies a lot and have big muscles in there, maybe it's, a little bigger than that, but it's about the ballpark. So if I were going to estimate how big a quarter was, I might say 2 seems reasonable. 3 probably is a bit much for the number of centimeters of a quarter, but definitely not 20 centimeters. That would be way too much. Okay. If you've ever seen TV shows where some woman's giving birth and they tell her you're so many centimeters dilated, the way the doctors figure that out is they use their fingers to figure out how big the opening is for the baby to come through. All right, a centimeter cubed is a milliliter. So if I were to take the end of my pinky and make it, about the same height as the width is, all the way around, that would be about a milliliter. Or about 1 miniature marshmallow. Now, we're not talking about those freeze-dried ones that they put in the hot chocolate packets that never actually turn into marshmallows. I mean, like an actual mini marshmallow. So if you, have the fluffy kind you throw on your hot chocolate, that kind of mini marshmallow, it's about a milliliter, sorry. A liter then is comparable to like a drink bottle. So normally if you get like a 20-ounce bottle of Coke, that's less. It's about a 32-ounce bottle, so a very large bottle. Your water bottles, that's pretty similar to a liter, to kind of give you that idea. So I could fit, this were about a liter, I could fit 1,000 miniature marshmallows. I could not fit 1,000 of these into 1 miniature marshmallow. That's going to help us later when we do a calculation. All right, temperature. Temperatures are important because we don't want you to get burned or frozen or whatever. So we have to think about when you're reading the thermometer in lab, how hot is something? So we're mostly used to using Fahrenheit. Celsius is what we do in lab. Later on in the semester, we are going to get to thermochemistry where we have to use Kelvin. So we're going to talk about Kelvin as well. Hopefully my battery is not going to die while I do this. Okay. So I'm giving you some benchmarks. Fahrenheit is sort of designed for the temperature ranges of the weather in US and in Middle Europe, not Scandinavia. 100 degrees is a hot day, 0 degrees is a cold day. Celsius is more scientific because it's based on things that don't change. So it's based on freezing point of water and boiling point of water. So what is the freezing point of water in Celsius? 0. That's our bottom. And the boiling point? 100. Okay, so that kind of makes that range sort of easy to remember, but we kind of have to tie that back to, well, what's going on with Fahrenheit? What temperature does water freeze in Fahrenheit? 32. So when the temperature starts dropping into the 30s and 20s overnight, people who do a lot of gardening might say, oh, I've got to cover my plants. I got to protect my plants because if it gets below 30, then you might have plants freeze. All right. Fewer people know this, but usually there's at least one person. What temperature does water boil at in Fahrenheit? 212. So when you are, making some cookies in the oven and it like everything bakes at 350 degrees, that's well above the boiling point of water. So this is why some dishes say cover the dish so you're not boiling away the water in the dish. If there's like a casserole or something, you don't want that to boil away. But things that you want to dry out a little bit, you don't want soggy cookies, then you leave them uncovered so that it can dry out. Okay, so how do we get between these things? Well, the size of Kelvin, and I forgot to say this before, we say degrees Fahrenheit and degrees Celsius, but it's not actually degree Kelvin, it's just Kelvin. I don't care if you say degree Kelvin, but some people harp on it. To get from one to the other, the size of a Celsius and the size of a Kelvin are the same size. So that difference, the difference between 0 and 1 degree Celsius and the difference between 273 and 274 Kelvin, that's the same amount. So we're just going to add the number 273. So why do this? Why make these huge numbers? Kelvin is an absolute scale. We're going to need that when we talk about gases. which means it measures something that has an actual property. In this case, the motion of the molecules. And when that property gets to zero, our measurement gets to zero, and there is no negative. So I can't have a -5 grams. It doesn't make sense for something to weigh negative grams, right? In the same way, once something stops moving, I can't have negative motion. So we have an absolute scale. That gets used in our unit on energy and in our unit on gases. Okay, so we're going to add that. Technically, it's 0.15. Sometimes I've seen 0.16. Usually our thermometers only go to that first decimal place. So sometimes I just ignore the 5 part of it because you can round it up or down. All right, room temperature. If you are a chemistry textbook, room temperature is 25 degrees Celsius. That is warmer than most people like to have. That works out to about 77 or 78 degrees. In the US, we tend to keep our rooms somewhere between 70 and 75 degrees, but there are places in the world where that is more normal. This number will come up again when we start using Kelvin as 298. So we will see that from time to time. In actuality, what's more comfortable for us in that 70 to 75 range might be 21 to 24 degrees Celsius. As I mentioned, safety is important. We don't want you to get burned. So how hot does it have to be for you to burn yourself? Well, it depends on how long you're touching something. It used to be that in the US, homes would have their water heaters set to 140 degrees. So the idea was you can kill germs at 140 degrees. But that would also burn people. And very old homes would have 2 separate faucets for the hot and the cold. So if you're trying to wash your hands in warm water, it's the middle of the winter, and so you turn them both on, you got one that's going to burn you and one that's freezing. So that wasn't a great idea. So now legally water companies are not, or the people who install the water heaters are not supposed to put it above 120. Can you get burned at 120? Sure. If I stick my hand in water at 120 degrees and leave it there for an hour, I'm going to get burned. It's going to hurt enough, I'm not going to leave it in there. But if I stick my hand in there for a few seconds and pull it out, no, it'll be uncomfortable, but it's not going to burn. I'm going to put 130. So that's a temperature that if you touch it to see how hot it is, probably it'll hurt, otherwise nothing will happen. You won't notice it later. But if you try to pick it up and are trying to carry it, not only is it going to hurt, it is going to leave a blister or something. So anything that's that high, you're not going to want to touch. This is right around 60 degrees Celsius. Okay, so if you're doing something, you got a boiling water bath and it starts to cool down and it gets down to 70 degrees and you're like, oh, I can pick that up and dump that out. No, 70 degrees is well above this. You're going to hurt yourself. If it gets down to 50, you might be able to pick it up, but it's going to be uncomfortable. So if you're just picking it up to do this, you can do that without too much trouble. But if it's 60 degrees, just wait for it to cool down. We'll use some gloves. How do we get back and forth between these two? So to go Celsius to Fahrenheit, if I'm thinking about temperatures that are kind of in this 100-degree range, I just use double and add 30. So if I were going from, say, 20 degrees Celsius, double 20 would be 40, and then add 30 would be 7. So it's right in that ballpark. What if I want to be more precise? I'm actually going to use 9/5, 9 divided by 5, so it's very close to 2. 9/5 of the Celsius temperature, and then I'm going to add 32. So if I take my 20 degrees and multiply that by 9/5, 20 divided by 5 is 4. 4 times 9 is 36, plus 32, I get 68. So it's not exactly the same. I said 70, it's actually 68, but it's close, right? So that's a good ballpark way. If I'm going to go in the other direction, I'm going to do the Fahrenheit minus 32 times 5/9. Now notice the Fahrenheit minus 32 is in parentheses. Our order of operations, you might have learned PEMDAS, or please excuse my dear Aunt Sally, the P is parentheses. That's the very first thing we do. You have to subtract off that 32 before you do the 5/9. So let's say I was doing 82 degrees. So 82 divided by, or subtract off the 32 gives me 50. And then I would take times 5 is 250, divided by 9 is something I can't do in my head. 60 something. I don't know. No, it wouldn't be 60 something. Shouldn't try to do it in my head. Okay. Anyway, that's how you do those calculations. Okay. Questions on that? All right.